Okay, so we have two more opportunities to discuss today. One is this morning for a couple of hours. I want to talk about very recent and current research activities that have been going on in my group that relate to everything we've talked about in the past week. So we won't talk about particle flows, even though we'll connect to that at some point, but we'll talk about interface tracking. We'll talk about the numerics of interface tracking. We'll talk about also quite a bit of work we've done recently on the prediction of spray formation. So we'll make use of very similar techniques compared to what we were talking about yesterday afternoon, and we'll just scale them up to larger meshes and many cores, and we'll see what we can get with that. Okay. So this comes from a recent presentation. So first of all, I think this is not in your course pack. So again, like I've said, I'll collect everything that we've talked about. I think pretty much only the Saturday morning presentation last week and this morning's presentations are missing, as well as all the notes I took during the afternoon. The fact is that I wrote all this down, so I can also collect all this as PDFs and send that to Professor Day, who will then forward that. So we'll have a whole collection of notes for this, at least after the fact. So this comes from a fairly recent talk I gave at Safran Tech, which is the research arm of the Safran engine company, which is a French company building essentially gas turbine engines, but aircraft propulsion systems and lots of other things. But that's their main business. So again, there's a bit of a slant towards the liquid being a fuel, typically a jet fuel, and the gas being thought as an oxidizer, and this entire system being looked at for the perspective of combustion. So we'll talk about methods first. So I'll try to connect to what we've talked about so far. I'll tell you this we've done, and this is missing, this is missing. We'll bring all this together and do some very brief verification, and then spend a bit more time talking about validation. And then we'll open up with a number of new directions, both from the perspective of adding more physics to those two-phase flow solvers, and from the perspective of improving the numerical methods. So we'll try to branch out in a number of different directions from there. And that should take us pretty much our entire morning. This afternoon, we'll be wrapping up with what's missing. A couple of things that we didn't have time to do. So some of that is the end of this chapter 7, so what we were talking about yesterday morning. We'll wrap this up quickly. I've been meaning to talk to you about an alternative, cheap way of improving mass conservation for level sets. So we'll derive that quickly, and I'll show you quickly the performance in comparison to a volume of fluid type of technique. And then we'll branch out again by looking at turbulence, by looking at compressibility, and by looking at electrohydrodynamics. So on each topic, we're not going to go into the details, but we'll talk about some of the overarching questions and what some of those techniques can help us. So that's the plan for the next few hours. Okay, any questions before we start? All right. So I think I showed this already. We're interested in multiphase turbulence. I'm interested in multiphase turbulence because it's a limiting process in a lot of engineering applications. And so that makes it a big challenge, but a very exciting challenge as well. So I'm not going to spend any more time on that. We'll zoom in directly to this typical, well, I think I showed that on the very first day, so we don't need to spend too much time. But if you're looking at the spray combustor, or any type of gas turbine engine type of system, if it's liquid fueled in air breathing, it's likely that The combustor is going to be a collection of little nozzles like that, spewing out liquid fuel, and then with an anchored flame right behind in one way or another. This comes from an experiment by Chris Edwards' group in collaboration with Tom Bowman at Stanford from about 15 or even almost 20 years ago that was sponsored by NASA. The point of this was to look at a true, well, a very highly simplified combustor. So it was just a canister, single nozzle type of combustor. And the, let's need some tuning, this engine here. But the idea is you have so this is a swirl system, so this is a swirl stabilized flame. And the specificity of it is that they embrace the two-phase flow nature of the problem by actually injecting liquid fuel. Specifically, this was N-heptane. So the question when you look at something like this is, can we model this computationally? And the answer is mostly yes, but one of the big questions is this. It is difficult still at this point for us to make proper prediction as to what the drop size should be, what the characteristics of the spray should be, and essentially how to predictively model this on in the context of CFD. And so at this point, either phenomenological models like we've talked about yesterday are used, or experimental data, essentially measurements coming from experiments at some location are taken as an input condition for CFD simulations. The problem with that obviously being that we're not predictive. If you need to know the answer to part of the problem in order to build an answer to the rest of the problem, you're not truly predictive.
Sure.
Yes?
Is there any solver available in the entire community where it can solve the entire problem? Like we have a fuel injection from the nozzle.
So entire problem including this part?
Yeah.
No. No. Well, okay, I guess it depends what you mean by solve. If you accept crude models here, then yes, there are solvers like that available. If you don't allow for, if you want a truly predictive model for what's happening here, the answer is no. This has not been integrated into a single solver yet.
So it's just still wide open problem.
Well, wide maybe not, but certainly open, yes. There's no answer as to how a fully predictive treatment of that region might look like so that it could then be integrated in a full turbulent combustion CFD tool. To be clear, if you inject a gas here, then there's a number of research tools available that are capable of tackling this entire problem. So the multi-phase aspect here is the source of the extra difficulty. So yeah, there's a lot of opportunities, and that was kind of my conclusion for today, that this is an area where there's a lot of growth to be expected in the near future. I think I showed that before. So you know, my perspective on this is, so I'm doing computation, so I'm interested in exploiting or leveraging those type of computational resources like this Titan supercomputer or others in order to try to help solve this problem. You know, this problem is as valid a problem as any others, and so let's have our facilities, nationwide facilities, to go after it. There's two perspectives to the use of CFD from my perspective. One is to use CFD as a discovery tool, wherein you essentially set up direct numerical simulations type of problem. So you go after the physics by setting up scale resolving simulations. This allows you to essentially substitute yourself to experimentalists, and you can then explore the true physics of the problem just, by just looking at what equations predict. That's one approach that's been mostly what I've been involved in. So the goal here is to elucidate the physics, generate data sets that can be used to then extract model simplified representations of the physics. The other perspective is the one that would really matter more in the industry, and that's putting together CFD tools that have sufficient predictive capabilities, but cost so that they can be used as part of the engineering design process. So this is your typical commercial CFD solvers, which are not scale resolving typically, and they will model a significant fraction of the scales in the physics through crude assumptions or well-tuned models, but characterized enough and understood well enough that we can rely on those to make predictions and therefore help guide engineering design. This part, I would argue, for multiphase flows is lacking. This is something that, again, that goes back to this comment here. We don't know how to do engineering design over this entire thing from computations. This is not a solved problem. This is a problem that is still open. However, I would argue that we can use CFD to help us elucidate what's going on right here. And that's a necessary step to help us build useful models down the road. So the way we're going to structure today's discussion will be the following. First, we'll spend a little while on the numerical strategy. So I'll try to connect to everything we've talked about so far, point out where things are exactly the same as to what we've discussed and where things are a bit different. So hopefully this, after all we've done, this will make a lot of sense. Then we'll do a few case studies. So essentially, after having looked at those tools, we'll ask ourselves how well those tools perform. So a few of the questions we'll ask is, well, first of all, are those tools performing up to our specifications from the basic mathematical derivation we went through in the past few days? Can we verify that the behavior and the performance of those tools is appropriate? And so that will be the verification exercise, and we'll spend fairly little time on that since we kind of went through, even though we didn't do that quantitatively, we looked at canonical verification tests in the past few days. But then we'll move away from that and we'll say, well, assuming that we verified our tools, let's validate our tools. So how well are those tools, how well suited are those tools in order to capture the physics of spray formation? Again, the main angle here will be this atomization question. And so for that, we'll need to compare against experiments. And so we'll look at two cases in particular. We'll start with a case that we won't go too deep into, and then we'll talk about two more cases from there. And then we will talk about possible next steps, interesting possible directions to improve on what we've been doing. And then we'll wrap up. So before we do that, let me reemphasize the importance of the spray formation to combustion processes. But in general, I would say that sprays are a very, very important aspect of multiphase flows. They are important in painting, agriculture, manufacturing, spray drying for food industry, firefighting. The list is long, so this is a key aspect. We'll zoom in a bit and simply focus on this problem again. So we'll be interested in fuel sprays for combustors. But all we're doing here can be transposed to many more types of applications. So there's really nothing ultimately that will tie us to a combustor. But within a combustor, the importance of a spray comes from the fact that the characteristics of an atomizer will ultimately control the drop size, the drop location, the drop velocity. Basically, it controls everything about where the fuel ends up going in your combustion chamber. The combustion that happens obviously in the gas-based environment, so we need to go through evaporation, but the stage is entirely set by the shape, the size, and the velocity distribution of the spray itself. So through the evaporation process, the spray ultimately is what controls the efficiency of the combustion process, the stability of the combustion process, the pollutant formation in the combustion process, et cetera, et cetera. The list is long. So this is a key precursor process. Right now, again, our modeling capabilities in terms of turbulent combustion, it's pretty good. Even, I would say, using large eddy simulation type of techniques, what's going on down here after the spray has gone? We're doing essentially a very, very job today at predicting that. There's work to be done still, but there's been enormous progress. But the quality of those predictions are entirely tied to the quality of the predictions of the initial condition of that process, or the boundary condition of that process, and that's the spray. The situations where, so those are large-scale perspectives on how things work. You can also come up with very concrete examples where the spray is the obvious critical thing that is limiting the development of a tool. Here, for example, consider as a tool a scramjet, a supersonic combustor system used for extremely high-speed propulsion. So a scramjet is a supersonic ramjet engine. It's a system where it's a combustion system that is characterized by the fact that you have no moving parts. So you rely on the fact that the flow goes fast enough that you can simply manipulate the flow passage in order to obtain a compressed, a higher pressure incoming flow. And then you can inject fuel in it, you can ignite this system, you can get combustion going, and that will So it's a very simple design that is supposed to work very well as soon as the engine itself is moving very fast. As soon as you can feed it enough air, it should work very well. So for supersonic or hypersonic propulsion, that can be a very interesting strategy. Concretely today, the main application is in the military realm. Obviously, we don't do a lot of we don't transport a lot of people at extremely high speeds, but we do transport missiles at high speed with engines like that. So if you're interested in the operation of a scramjet engine, what ends up happening in the system is the energy density of the liquid fuel is so high that there's just no question. This engine needs to be liquid fueled. That doesn't mean you can't build something that's not liquid fueled, but the extra efficiency coming from the energy density of a liquid jet fuel type of fuel is just undeniable. So if it is liquid fueled, well, if you assume that the system is already working and you already have a flame and you already have a combustion, what you can do is, so imagine this thing was, so this is cold right now. Imagine you had the flame down there, you'll have a lot of heat available. You can circulate your liquid fuel next to this scramjet passage, collect all that heat and evaporate your fuel. And then you can bring this fuel back and inject it in your combustion chamber in gaseous form. So that's fine, there's enough. In fact, you can do away with the entire atomization process and evaporation process by pre-vaporizing your fuel thanks to the combustion heat. So that means you can study this problem in a gas phase environment entirely, and that simplifies the problem enormously. The issue is, to do this, you need to assume that the engine is running already, that the combustion is going already. So now the real problem becomes, how do you start up this entire thing? So you have a fast-moving missile, or whatever you want to think about, commercial aircraft transporting passengers in the hopefully not too far future, and you want to start up your engine. You have no extra heat available. You have to deal with the liquid fuel injection problem. And now you get into this configuration. There's a high-speed flow coming from left to right here in this passage. Typically, for a typical engine, you'll be between the Mach 1.5 and 2.5 or 3, something like this. So not crazy Mach numbers, but you have certainly a supersonic flow coming from left to right. That means that the residence time in your scramjet is going to be very tiny. And during that time, you need to. So this is what's going on here. There's a tiny nozzle, and there's a liquid jet coming in, atomizing into a spray that looks very cloudy, but this is just because of the lack of temporal resolution. So this is just a collection of tiny droplets. Your spray, you need to evaporate it, and then you need to, this thing needs to combust. Well, that's tough because you have very little time and distance for this entire thing to happen. And in addition to that, this process itself is not well understood today. It's difficult to experiment on, and there's very few computational tools that would allow you to directly solve what's going on right here. And yes, you can use Lagrangian models, and you can use correlations for drag on the droplets that depends on the Reynolds number and the Mach number. And yes, you can do lots and lots of things. None of these really go down to the problem of what controls the physics right here. And again, that takes us back to the question of the predictive or lack of predictive nature of existing atomization models. In fact, experimentally, so this comes from the Air Force Research Lab at Wright-Patterson. They have a testing facility there in which they're injecting here water, and you can see that it's possible for the system to become. You can see this pulsation here. The jet is kind of pumping up and down, and it releases packets of droplets downstream. So as you can see, the unsteadiness of this is significant. Now the question is, how do you ignite a system like that? Well, you would want to be sure that you have a combustible mixture somewhere downstream. If your jet is wobbling around and releasing packets of droplets, it's very difficult to know whether, say, you shoot a laser in order to ignite your combustor. If you shoot it right in the middle here between the two packets of drops, you're not going to burn. So again, we need to study this and figure out what's going on. So we can talk briefly about how you form a spray. So this is more of the very applied research or more engineering question. If I want to create a spray with certain characteristics, what do I do? Well, there's a lot of techniques. This comes from a book by Chuck Lipp called Practical Spray Technology that goes through the art of choosing and tuning an atomizer. So this is a very applied question, but it's an interesting question. So first of all, the simplest thing you can possibly do to create a spray is to push liquid out of a little hole, like a little nozzle like this. So you have a cavity, you dig a hole in this, you push fluid through that, you'll form a spray. So this is what you would call a pressurized injector or pressurized atomizer. It is, again, we talked about this problem yesterday from the simple perspective. You need to form a spray, you need to increase surface area. That means you need to get energy from some sort and transfer it into surface energy. That the source of the energy in a system like this is simply the kinetic energy that you impart to the liquid. So you hope that the high kinetic energy in the liquid can be transferred, will naturally get into the high surface energy of your liquid in the form of an increased surface area. You can start to shape this type of thing. So you can make it V-shaped or tune it in any way to generate a certain pattern for the jet that comes out. So that allows you to spray at a certain known angle. Those techniques are pretty basic. The only parameter here, the only thing that you control is the pressure, meaning the velocity that you're going to impart to your liquid. So that doesn't give you a lot of control. People have realized that if you start to spin the system, if you start to swirl your liquid, you can provide a lot less kinetic energy to your flow and still have pretty good efficiency. So that gives rise to this idea of, yes, you just pressurize your liquid, but you impart angular momentum to it, as well as linear momentum. So that gives you pressure swirl atomizers. So all those type of techniques, this is your typical nozzle for painting applications, for example. This is the very low cost, easy to clean, easy to replace nozzle. This is used for many applications as well. That's pharmaceuticals and the food the food industry and things like that will use pressure swirl atomizers. People have also realized that if the goal is to increase surface area, one way of doing that is enforcing the flow to follow an imposed geometry by flowing along a wall, forming a film along that wall, meaning reducing one of the length scales of your liquid flow in order to promote breakup. So if you send a jet of liquid against the wall, you'll form a thin film, and once the wall terminates, this thin film will continue because of its initial momentum, its inertia, and now you have a small length scale. If the sheet becomes unstable, you'll form a spray with a size controlled by the thickness of the film. This is the type of thing you see quite a bit in the realm of agricultural spraying, for example. If you combine those ideas together, you can spray against the wall, but also shape your wall such that you impart swirl to liquid, and that gets you into this type of design, which is a spiral nozzle. This is often used, and again, I don't know where the fire extinguishers here are, if there are any. I would expect they are just hidden above this fake ceiling, but this is a typical design for firefighting. Ultimately, all those things are not that tunable. The only thing that you can do is flow faster or slower, and you don't have an enormous amount of control on what's going to come out. So people, try. This is an art to try to design something that looks good, and then you flow through it and you measure the performance. The nozzle manufacturer will report the drop size and the spray angle, and then they'll report the characteristics as a function of the flow rate through those nozzles, and that's essentially it. If you want to have more control, you can start to think about how you can flow simultaneously gas and your liquid. And in particular, suddenly you might realize that there's a lot of benefits from doing something like this. So say you're interested in you're looking at a car at a diesel engine on a truck, for example. Well, this is a reasonable approach because it's not that complicated to pressurize your liquid. So you can fairly easily transport this with your engine a system that will allow you to reach a high enough pressure to have high injection velocities. But it's not that easy if you're interested in injecting a high pressure liquid and you're looking at the gas turbine engine for an aircraft. Suddenly, it's not the most exciting thing to do to reach really high pressures for liquid fuel on a flying machine. However, you have a lot of high energy air available around you. So that's not that difficult to imagine imparting a lot of momentum to a gas. So that takes us to this idea that we've discussed in the past few days. Instead of putting the momentum in your liquid, you can leave your liquid with a low momentum but impart the momentum to your gas, and if you flow them one against the other, the gas should be in a position to break up your liquid. And that gives rise to those two fluid atomizers. There's lots of different variations on these ideas. Typically, this is referred to a gas-assisted atomizer, where the gas assists the atomization of the liquid, or it can also be referred to as an air blast atomizer, where the air is blasting away the liquid droplets. So because of the extra control right now, you can tune the flow rate for both differently. You can get this to perform well over a fairly wide range of conditions, and that tends to be the preferred strategy. That plus typically you'll combine swirl to that, or you'll combine the idea of forming a film, but that tends to be the preferred strategy for flying systems, aircraft gas turbine engines in particular. So that's what we're going to look at. Configuration. So again, if you're looking at an aircraft, you'll typically end up with a nozzle that looks something like this. So in a system like this, and we'll look at this guy some more, but this is a turbomeca nozzle. There's in this system there is a liquid flow and there's a surrounding gas flow. I guess vice versa, I can't remember. But you're co-flowing the two phases simultaneously, and also the ports here are off the side, so this is a swirl system. So you'll either swirl the gas or the liquid or both, or you'll swirl one in one direction and the other one in the other direction. So this is the typical type of design. Now, a system like that, now we're going to ask it to work well under a wide range of parameters. So I just collected a couple, or I guess 3 here on the table. This comes, I have an inside mold. Vincent Moreau at Korea was working for Turbomeca for a number of years, and so I had access to, through him, to a lot of very interesting discussion regarding what really matters in the end application, in the real gas turbine. But so if you look at the operating conditions of an aircraft, or a gas turbine engine, an aircraft gas turbine engine, you can identify different points of interest. One would be an idle performance. You can look at cruise conditions, the high power, full power takeoff conditions. Well, one of the most limiting for the design of something like this would be the reignition or light on at high altitude. So imagine for whatever reason, an engine just stops as you're flying. We define those numbers already. We'll look here, because we're saying that this is the gas that carries most of the momentum. We'll focus on the gas Reynolds number and the gas Weber number. We've defined those guys already. And this is the tough condition. Why is it the tough condition? Well, because the temperature of the entire system is very low. That means that the viscosity, not the viscosity, but the effective, the Reynolds number doesn't care too much about the ambient temperature, but the Weber number will typically have lower velocity flows, and so we have less of a capability here. Basically, if the engine is just starting, we have cold air, but the system is not pressurized anymore. So the density here is going to be the lowest. The density of the gas upon reignition conditions is going to be very low. And so we're going to be working with a gas Weber number of 20, 30. So if you remember some of what we discussed about yesterday, this is the bare minimum for achieving breakup. So this means that we'll have to be careful, and we'll expect to have lots of big drops that will splash around on the walls of the combustor, and things may not look very good for a little while. So overall, this process, I would argue here that ideally we would want to control it. We're not at the point where we control it in a fine way, and certainly not in an active way. But we should get to that stage at some point, or at least we should strive to go to that stage. So let's look a little bit more in details at what this looks like. So if I take a canonical 2-fluid atomizer, this is a design that comes from Alberto Eliseda at University of Washington. And so this is a simple central liquid passage that's essentially a straight passage, and then there's a shaped nozzle, annular nozzle of gas that surrounds it. You can see how this looks at the flow. As the flow comes out, we form our spray. We have this thing flapping around a bit and breaking up. So here's a list of interesting questions to which I don't have an answer, and I think for the most part people don't have clear answers. What is the effect of overall the nozzle geometry and the flow that comes in on the spray characteristics? People have very ad hoc answers to this. Let's change the nozzle and measure what comes out. But there's no comprehensive theoretical understanding as to the connection between those things. So that could be, would it be better or worse to put turbulence in the liquid? Should the liquid come out with? Should we try to put elliptic shapes, or how should we adjust things here? Should we swirl the liquid? Should we try to flow it fast enough that it cavitates? Same questions for the gas. what is the appropriate gas boundary layer thickness that would maximize the breakup? Should it be a turbulent gas or laminar gas? What should the flow rate be? And at what angle should I hit the layer to maximize or to optimize the spray I get? So all this suggests that there's a lot of opportunities for at least passive control strategies to improve a spray, and potentially also active control strategies. So at the very least, a couple of passive ideas would be to tuning properly the gas boundary layer characteristics to obtain the type of breakup you want. Also just designing a nozzle that has a material with the proper surface energy, the proper wettability to maximize breakup. If you want to think about active control, well, what about acoustic pulsations to try to excite certain modes and waves and enhancing breakup? How about using electrostatic effects in order to try to promote breakup as well? Those questions are, I think, deserving of a lot of attention. So, from a theoretical standpoint, you can study this problem. We've talked about that. Typically, this takes the form of linear stability analysis studies, kind of an almost really tailored type of analysis. This is all fine and good. There's a lot of work that's been done, published by lots of people. I'm citing a few here. Zaleski has done quite a work on that. Prosperetti has done a lot of work on that. And Philippe Matas has done a lot of work on those questions. But the idea is, like we did together on Monday, you have to prescribe some sort of a simple base flow, and from there, and typically it's going to be a parallel base flow, and from there you're going to look at the stability of this flow. You can solve that analytically. The problem is that most realistic flows cannot be boiled down to a simple study like this. And so this is interesting and exact, or at least semi-analytical. So it will tell you a lot about the physics, but in very limited configurations. Obviously, we rely on experimental techniques, but there are also significant challenges there. The typical approach is to rely on light scattering techniques, the simplest one being simple shadow graphs. So you look at what is the shadow formed by your spray, essentially. It's all fine and good, but this is a very complicated type of data to analyze. In particular, once you go to high enough Reynolds and Weber numbers, you have a spray that starts to essentially encompass the entire atomization region. And so if you image your spray, what you'll see is the outer shroud of droplets. You won't be able to see the atomization process because it's obstructed by the presence of lots of drops. So there's a simple question here of optical axis. If you're forming a spray, you probably cannot look inside the region that forms the spray using light scattering techniques. Fairly recently, a number of techniques have been proposed that are based on non-scattering techniques. One of them being simple X-rays, right? If you have a high enough power X-ray source, you can simply shoot a high-speed X-ray or perform a high-speed X-ray of your jet and look through in a line-integrated sense. So that's what this image is. That comes from work of Kastengren and Ted Heindel at Iowa State University. But that allows you to look at everything in the atomization region. You go through the drops and you look inside. The issue is that this is not a particularly simple thing. In fact, this image was generated during a one-week experimental campaign done on a synchrotron X-ray source at Argonne National Lab. So that means essentially taking a spray setup and the corresponding wind tunnel and all this, putting that on a truck, bringing that on a synchrotron facility, and then fitting all this little hutch of the size of a small room, essentially, and then performing an experiment while you're shooting a very deadly and high-intensity X-ray at it. So that's a complex process. There's alternatives. For example, here I'm talking about ballistic imaging. This is an idea of gating your light such that you only collect the photons that have not been, of which the direction has not changed as they've gone through the liquid-gas interface. So by simply looking at the speed of light and the distance that needs to be traversed, you can estimate when to open and close your window or your eye in order to look at only the photons that have shot straight through the spray. That allows you to image deep inside the spray. This is also a pretty complicated technique. This ballistic imaging is also a pretty complicated technique. The main person there on that technique is probably Mark Linne, who is now at University of Edinburgh. All right, so the alternative to all this is simulations. And here again, I'll distinguish between scale resolving simulations. I'm not talking really, I'm like talking about direct numerical simulations, which is the accepted term for a simulation that resolves all scales in a single phase environment, because we've already argued that the topology change event is not something that is contained in Navier-Stokes. If I were to fully resolve all the scales of Stokes two-phase model, I would not see breakout ever, and the smaller scales would be infinitesimal in size. So the concept of DNS is a loosely defined concept for two-phase flow. So instead, I want to say scale resolving simulations wherein we acknowledge that there's this breakup that is hand-waved in some way. And for that, my argument here is that good methods exist, accurate methods exist. They'll be limited to fairly limited range of scales. And that's a struggle in terms of how do we push this to engineering relevant conditions. And then the alternative is the scale model simulations, engineering simulations, RANS and LES type simulations wherein you model the breakup. But the question is, how do you do this? So the example here, this is a sigma Y simulation. The sigma Y is one of the few RANS models out there that attempt to fully model the breakup process, the primary breakup process. And so I've cited here Borghi, and there's a few more people. Lang Hall also has some DNS model of atomization, some LES model of atomization. Gorokovsky has models of atomization. But those, none of these models have been truly validated and extensively proven yet because of the lack of data and the lack of understanding of what is truly the correct solution. So this is very much work in progress, and for us here, we're going to focus on this part. Now, in terms of how we do all this, well, we talked about those techniques fairly extensively already. There's two big steps. What do you do with the interface? So you can use level set method, fluid method, front tracking method. I've kind of highlighted what I think is the main advantage about each of them. You can hybridize them with one another. You can adjust things to find the optimal combinations of those methods. But for the most part, those are the three big classes of methods out there. And then the question is, how do you couple the information of where the interface is to your flow solver? And there's really here two big overarching strategies. Either use a sharp interface representation. This is, for example, the ghost-free technology we've used 2 days ago, where we truly derive a jump condition such that we discretize with the known presence of a discontinuity in our flow. Or you can spread around your discontinuity over a few cells and discretize through it by saying, well, it's as if we were looking at a single-phase fluid. What I'm going to show you will be based on volume of fluid combined with sharp interface models. Okay? So let me go through the techniques quickly, because a lot of them you know already. So for now, this afternoon we'll lift a lot of those conditions, but for now we'll be incompressible isothermal without phase change. So we're interested in the three following equations. We wrote them already. This is the sketch of the local configuration. First of all, this is our material transport of the interface. In order to deal with this, we're going to rely, like I just said, on the volume of fluid technique. Which technique? Well, it's going to be a 3D unsplit VAF scheme. Unsplit, we talked about that yesterday afternoon. We contrasted that to the split approach. The method that we have is second order accurate, formally bounded, and exactly mass conserving. So we're not going to be losing or gaining any mass as we transport. We're not the only ones to have thought and considered techniques like this. Le Chenadec is an important variant. I guess our method is a variant of the Le Chenadec method that was a little bit before ours. And this is more directly what we implemented yesterday, right? This idea of moving forwards in time and finding the volume in there. And there's a few other people who've proposed similar techniques. Our claim to success here, or to fame, is the fact that we're exactly mass conserving with this. The coupling with the flow solver, essentially the handling of the discontinuities, such as this sigma kappa, we're doing that using a ghost fluid method. So this is exactly what we derived together 2 days ago, based on the work of Fetkiv et al., initially in a compressible environment, and then Liu, Kang, and Fetkiv, so a couple of students at Fetkiv a few years, well, I guess 1 year later. The resulting system we need to solve for the pressure is ugly, and we talked about the fact that it's a difficult, essentially very ill-posed Poisson problem that we need to solve. This problem, we found very good success dealing with it using a so-called black box multigrid scheme. So this is a specific type of linear solver that is extremely well suited, in fact has been designed to deal with highly discontinuous Poisson coefficients. So, and the author for this is Dandy, who was an applied mathematician at Los Alamos for several decades. So, and he has a number of publications in which he lays out this strategy. So we would need something like that. That's one of our missing components in our solver right now. Solver is based on this simple conjugate gradient preconditioned by an incomplete Cholesky, or a somewhat improved Gauss-Seidel preconditioner, essentially. We would need to like that to guarantee good convergence, no matter what the density ratio is. That's something we completely overlooked, even though I mentioned that this was going to be a problem. We discretized this equation without caring at all about the rho. In fact, if you remember, we took this rho out and we brought it as a 1 over rho here, so that only our Poisson solver was to be modified when we coupled our level set to our flow solver. Well, if we do this, we're not going to be conserving momentum. And if we don't conserve momentum, that means that any situation where I have a high speed, low density flow interacting with a low speed, high density flow, as soon as I'm going to make any type of error in my relative transport, so as soon as I'm going to move or solve that equation differently as that equation, I'm going to be likely to create a region of high density, high velocity fluid, and therefore I will be artificially creating enormous amounts of momentum. If you solve this equation in conservative form directly, this cannot happen, and therefore you'll be stable. So in order to solve this problem, we're going to rely on the full a direct solution to that equation here, to those terms. They contain discontinuous quantities, so we're going to have to use a similar strategy based on Voff and Plick in order to solve this. And this is a very recent paper following an idea by Rudman that we use in order to conserve momentum with our scheme. We do that at the interface, away from the interface. It is not too difficult to be exact in momentum and energy conserving, so we combine different schemes close and away from the interface. So this is probably the biggest missing piece in the code we worked on together. And because of that, it will not be stable at high density ratios, nor would it be stable at with high shear across the. Any situation where the heavy phase carries the momentum, like the splash problem, things should be fine. Finally, we need to be able to deal with the geometry of the nozzle. For that, we're going to use a non-body fitted mesh using a conservative inverse boundary scheme of Mayer et al. And then finally, we'll say also that an implicit time integration is probably better. And the main reason for that, well, you saw it with the splash problem we looked at yesterday. Upon splashing, we create locally really high velocities as the gas has to rush out from this gap between the drop and the pool. That means that every time you look at fairly high density ratio two-phase flows, your flow is bound to locally accelerate very rapidly as soon as drops intersect or ligaments hit surfaces. You have those splash events all the time. Your velocity will spike up legitimately, right? It's not the code running unstable. It is legitimate that locally you should have rapid acceleration. If you're explicit, the code is going to crash. So all this let me see where we are with. Are we okay for the picture? Can we wait another 4 or 5 minutes? Shantanu? Okay. Okay, so let's bring all this together. I want to just go through some of those details. We've talked about that, so I'll go quick. But the idea is we will use a semi-Lagrangian approach based on strict tubes in order to calculate to do our VAF transport. We talked about that already. I'll just summarize the reasoning behind this. So first of all, imagine this is a liquid jet I want to solve. I'm going to identify that on one side I have gas, on the other side I have liquid through some sort of a liquid distribution function, chi, like this. I will average it over a grid cell. The zeroth order moment of this chi distribution of that grid cell is going to give me directly my liquid volume fraction. So I'm calling it alpha here. Liquid volume fraction on that cell, all right? Once I have this, this is a cell average quantity. I need to transport it using approach. A finite volume discretization requires the specification of alpha fluxes or liquid volume fluxes at the cell face. So now my question becomes, how do I specify this west flux of liquid volume fraction? Well, we talked about that yesterday, but I thought I should show you a very concrete example. If I use standard finite volume techniques, we'll either have to suffer a dispersive error or diffusive error. If I use a low order scheme, I'll typically have a dominant diffusive error, and then this is what happens to a simple droplet represented with VAF. If I use a diffusive scheme, I have now mixing taking place between my phases. I cannot represent accurately where my interface is located. But if I go high order, yes, okay, I counteract diffusion, but this is what happens instead. I have dispersive errors now. That means I'm going to have cells that are less than 0% liquid and cells that are more than 100% liquid. In the same way, I still cannot represent accurately where my interface is located. So we can't do that. We have to use something else. The something else is based on first the split calculation. So we know already how this works. We went through the details of that. I'll calculate first a normal, and knowing the volume fraction, I can now place in each cell a plane using the algorithm we worked on yesterday. Now in each cell, I'm going to know where my interface is. Now I'm going to look at my phase flux calculation by switching to this flux volume perspective. This gray area here corresponds to the entire region of my flow that during the course of my time step flows from the outside into cell I from the west face. So this is the same idea that we talked about yesterday, but we talked about it in a split fashion. Basically, we talked about it from the perspective of X transport and Y transport and Z transport. Here we're doing full 3D transport. We're emitting a full unsplit strict tube all at once from the face. This idea is not particularly new. Again, we talked about this on a split type of concept before. People have realized that a non-split transport would be better very early on. So the Ryder and Koth scheme, for example, looked at this idea of unsplit transport in 2D. However, the trick is you want to make sure that your strict tubes do not ever overlap. If they overlap, then you will have certain regions of your flow that will be transported twice. So any overlap is a problem. How do you avoid overlap? Well, you avoid overlap by making sure that you define your velocity used to build the strict tube at the cell vertices. This way you can transport backwards in time your cell vertex and form a perfectly coherent collection of flux volumes. And 3D, people have shied away from that. Even though the concept is not that complicated, right? You take each of, so this is a cell face, right? This is my west cell face. And each of the vertices will be sent backwards in time to give me my flux volume. Anything that lies in my flux volume at time n will be brought through that face into my cell I. So why have people shied away from this? Well, that's the reason. When you sketch it like that, everything looks fine. But this is a completely acceptable shape for your flux volume. Things crossed, you can get negative volumes. Things can look very, very ugly. So you need some smart library to deal with the complex geometrical operations that fall out. But I'll show you that, in fact, this is not that complicated. So imagine I have my face AB in 2D. My flux volume, flux area in this case, would be ABCD. I've taken A back in time and made it D, and B back in time and made it C. This is the ideal situation. Everything's fine. I can say that this is a positive flux. I can use the right-hand rule to say that this is an OK positive flux. But I could also have this region. This is an equally valid flux that I could be building. In a situation like that, this stuff flows into the cell. It's a positive contribution to my flux. But this region here, well, conceptually it is still fine. It's just a region that actually flows out of my cell. So it's just a negative contribution to my flux. Well, it turns out that if you work with simplices, like we were talking about yesterday, you can deal with that efficiently as follows. So if I take this guy and split it in simplices, in 2D a simplex is a triangle, I have a collection of two triangles. If I order them appropriately, they're both positive, they both contribute to flux coming into my cell. Fine. If I use the same exact ordering and look at what happens here, I have now triangle ACB. This is a positive triangle, but it includes this region that is not part of my flux. This region should not be part of my flux. So this guy is wrong. It contains some of what I want, but also stuff I don't want. But look at the other. The other is ABC. Sign is flipped. It contains what I want, but also more than what I want. But the extra stuff it contains is exactly the same extra stuff that the other triangle contains. So basically, this is handled positively, negatively, and this is calculated twice, both positive and negative. It will cancel out. So in fact, what I'm saying is those crossing events, they're not that difficult to deal with as long as you're consistent with the ordering of simplices. So you can digest all this in a fairly simple and systematic way that makes it, in the end, fairly approachable. So ultimately, you end up with a scheme that should be 4 millisecond order accurate, perfectly bounded. We can fix a number of things that I'm not mentioning here to have it exactly conservative. And so this is an example of a test. Instead of doing this circle deformation, you can put a droplet in turbulence, deform it, flow it back. You have a second order converging shape error, zero mass error, zero boundedness error. So we'll talk about a few additions to all this. And just to summarize, the flow solver that we get is also 4 millisecond order accurate. It conserves mass exactly, it conserves momentum exactly, but the kinetic energy, I don't know how to conserve it exactly in the presence of an interface. So away from the interface, I conserve kinetic energy. At the interface, I don't know how to do that. And then we scale it up on, we put that with MPI, and we can now run big simulations. And I'll stop here. We'll go take a picture. And when we come back, we'll talk about what this tool can predict.